Hey friends, welcome back to another video. It's me, Ashol the Brilliant, and you're watching Learn with Ashol. And today we're going to be talking about the second theorem of our chapter, our video series, which we have started, which is about the projection of a side of a triangle. It is the eighth chapter in the 10th grade Punjab textbook board's math book. And yeah, like the first theorem is about an obtuse triangle. It's used on obtuse triangles. The second one right here, this one, is used on acute triangles. So if you haven't watched the first one, I recommend you watch that first and then come back to this video. So yeah, you build your concept, and yeah, we'll be building our concept of the second theorem in this video. So without further ado, let's get started. First, we're just gonna read the theorem. So let's get started. It states that the square of the side opposite to the acute angle in an acute angle triangle is equal to the sum of the squares of the sides forming the acute angle subtracted by twice the length of one side, and the projection of the other. This is what the theorem states, and now I'm just going to cancel this because now we're about to work in what is the theorem and how do we apply it to an acute triangle. So first off, we're going to draw the triangle. So yeah, first let's draw a physical acute triangle. So I'm making the base big. Anyway, yeah, this is one, and let's go to this again, and let's make the other. So yeah, let's use this. This is like our acute angle, the one that we're going to be dealing with, and like these two lines, I mean, have formed the acute angle that we want to deal with. And yeah, let's use yellow. We haven't used that in a while. Let's see, where do these meet? They meet right here, or actually, do they meet right there? We can just attach it right there. So there we go. This is our triangle. All right. So cool. Let's call this triangle ABC. This is triangle ABC. I named it ABC. You can name it whatever you want, or in the test, if you have like some type of exam or any question in your book, it might not have the same triangle names, right? Like the point names, they might not be all the same, like over here. That's okay. It's just the matter of your concept. If that's clear for you, then yeah, it doesn't really matter what triangle it is, right? So what are we gonna do? This is our triangle, and the acute angle that we're going to be considering, that we're going to be dealing with, is this angle, angle A right here. So this is our acute angle that we want to be applying the theorem, in whose perspective we want to apply the theorem. So that means that we're considering this angle A, which consists of side AC and AB. And yeah, let's get to our theorem again. So now we have our triangle. Now we're gonna write the theorem as we read it and we draw it, and like yeah, we'll write it as well. So the square, first off, it says, oh, what am I doing? This, the square of the side opposite to the acute angle in an acute angle triangle. So what side is opposite? So here is our acute angle. This is our acute angle, angle A. So the side that's opposite to that, is this side BC. So side BC, the square of side BC. So we're writing the theorem right here. The side that's opposite to angle A is side BC. So BC square over here. Let's move on. It says is equal to the sum of the squares of the sides forming the acute angle So the sum of the squares of the sides forming the acute angle. What does that mean? Well, just before we started the theorem, I just told you guys, right, that angle A, which is right this angle right here, is made up of side AC right here and side BC right here. So I mean AB right here. So like these two sides, they are forming this angle, and that means that like the sum of these sides, the sum of the squares of these sides. So like the first side, right here. The first side is AB if we take, right? So AB square plus AC square. This is what it means over here, the sum of the squares of the sides that are forming the acute angle. AB, AB square, AC, AC square. Now, let's go over here again. Right, so like the theorem is done yet. It's this part is right here. Subtracted by twice the length of one side and the projection of the other. So, what is this? Twice the length of one side. So like twice, that means like minus 2 multiplied by the length of one side and the projection of the other. So what is the length of one side and what is the projection of the other? What is it talking about here? So like you can choose an axis, right? I'm choosing this axis. We normally look at it from this axis right here, the one that AB is on, right? It's the horizontal axis for us. Yeah, maybe just position it right here, so that it seems like a legit extension of line AB. Like what I'm trying to say is this is our axis, right? And that means like the side that's on the axis, that is the side that we're taking as the length of one side. So that's the length, that's the side whose length we're going to take as length of one side. So AB is, we're looking at it from the axis that AB is on. We're going to call that our horizontal axis. So then AB is the length of one side, and the projection of the other is this side right here, side AC. We need its projection to complete this theorem. So yeah, if this is like the theorem, if we don't have the projection, this is what it's going to look like. So there's like a question mark here, but like we're going to draw it, right? So let's draw it. I'm going to come down here. I'm just going to write better yet, let's just copy the triangle too. Please just, yeah, I guess we can take this and just move down and paste, bring it like right here, and yeah, as this obviously will seem irritating, I'll just erase that. Gone. And yeah, now let's come back here. So our construction, oh, look at that I. Yeah. Okay, so what are we gonna first do? We're gonna do the same thing as we did in the previous theorem, but like, yeah, like I mean, in the previous theorem I used the same triangle, so from that I mean we're gonna do the same thing we did. We drew a perpendicular from point C, if you guys remember. Yeah, I think you do if you watched my video. If you didn't, seriously, go right now, stop this, go watch that, and then come back to this. Anyway, draw a perpendicular from point C onto line segment AB, touching a point that we will call D. So this is the construction, that's all it is, and I will do it right in front of you guys right here. Let's choose a line, and this is point C. Like maybe we won't choose line. First let's just, yeah, identify. This is point C right here, and I'm about to draw a perpendicular from this point C onto line AB. There. This is our perpendicular, and I'm gonna make this dotted so that like it's type of like, you know, you can tell it's drawn, right? So yeah. Okay, so this is our perpendicular, and this point of contact of the perpendicular from point C with line AB, like the point at which they intersect, the perpendicular and the line segment, actually, in fact, line segment AB, we're gonna call that, it's not line, it's line segment AB, so we're gonna call that point D. So this point right here, this one right here, just colored it blue. I think we should leave it black. Anyway, yeah, so this point is called, or I called it D. You can call it something else when you're doing the theorem, and yeah, your choice. You can even make the triangle different if you want, but like, just make sure that it's an acute triangle, because this theorem is only applicable to acute triangles. Anyway, now now let's use this, and again, let's draw a line. So like, we drew the perpendicular, and that's basically all we needed for the projection. So what is the projection? The projection is this distance right here. This distance down here, I'm going to color it reddish. This distance is like basically meaning AD is the projection of the side, this side AC. So it was orange. AD, which is the projection. So just to like, let's just have like a quick recap, right, of whatever we've done up till now. Basically, we had a acute triangle, we named it ABC, and there was an acute angle, which happens to be angle A in our case, because we consider an angle A. And like, according to the theorem states that the angle, the side that's opposite to the acute angle in an acute angle triangle, the square of that side, which we have side BC, so we have BC square over here, is equal to the sum of the squares of the sides that are forming the acute angle. So we have angle A, that's right here, and the sides that are forming it are, as we talked before, AB. So like, this whole line AB, basically it's square, AB square, and AC square, so AC square, the sum of their squares. That's done. Then subtracted by twice, meaning -2, the length. By the way, let me just like underline these. Yeah, so AB and AC, these are the sides that are making the angle, so that's why I'm coloring them both red, like underlining them with red. Anyway, -2 into AB, which is the length of one side, subtracted by twice the length of one side. So that's AB. We are, like, from our perspective, we are looking at the horizontal axis as the axis on which AB lies. So AB is the length of one side in our case, and the projection of the other, which is AC, so its projection is AD down here, you guys know, that's AD right here. So that's the projection of this length. AD is the projection of AC. So yeah, that's pretty much it. And now it is time to prove this theorem. So let's get going. Yeah, so this image looks packed, so I think I'll just grab the previous one maybe. Yeah, let's just take we're just gonna work with this image, because the other one is well, a little cluttered with the colors, as you can see. Let's see if we can grab the theorem like a clean. Yeah, we can always erase the rest. So yeah, the theorem is right here, and let's just erase this. And anyway, yeah, so this is our theorem, and let me just grab our perpendicular. So yeah, this is our perpendicular, you guys know. So yeah, I'm just gonna leave it at that, and just draw a point here, and yeah, this is the point of intersection. Anyway, yeah, this is our triangle, and I want to show you guys something real quick over here. If you look at this, yeah, so this whole, maybe you don't even need to do, maybe we don't even need the zoom, but yeah, and probably get rid of this. Anyway, yeah, so now if you guys look over here, these, when we drew this perpendicular, like some new angles formed, if you guys noticed, and those were both right angles. These angles are 90-degree angles. And what does that mean? That means that we had an acute angle, and because we drew the perpendicular from, well, a point, we, like, it's perpendicular, and that means that it's forming a 90-degree angle with the side. You could say, like, you know, from here, from point C, when it went to when it intersected line AB, line segment AB, it made a 90-degree angle, which is this angle right here, which we're talking about. So what it did was basically it gave us two right triangles, and we're going to use these right triangles to prove the theorem, which is right here, as you can see. This theorem right here, we're going to prove this theorem using these right triangles. So let's begin. But like before we actually start doing that, actually like start proving the theorem, I just want to give you a recap of the Pythagoras theorem, or you could call it the PGT, which basically states, the PGT theory or theorem states that the square of the hypotenuse, and it's applied to right triangles, and what it states is that the square of the hypotenuse, which you can let h let the hypotenuse be h in any right triangle, the square of the hypotenuse is equal to the sum of the squares of the base and the perpendicular. And yeah, that's basically the Pythagoras theorem. Yeah, I was gonna say hypotenuse theorem. Pythagoras theorem. So if we look at these triangles, I just want to tell you guys, I just want to label the parts. So this AC, side AC for triangle, right triangle ADC, the side AC is the hypotenuse. So I'm going to name it H. And for the triangle BDC, this side over here is the hypotenuse. And for ADC actually, the base is AD right here. Or maybe this is not a good color because it doesn't really pop out. So yeah, this is a good color. And yeah, so AD is the base for the right triangle. I'm going to name it B for base. For the right triangle ADC. And for the other triangle BDC, BD is the base. But they have different hypotenuse and different hypotenuses and like bases, but they have one thing in common. Can you guys guess it? Yeah, there's only one thing left actually, in fact, but yeah, they share the same perpendicular, which I'm gonna label by P. So yeah, like CD, its length is not gonna change for either triangle. They have the same length for their perpendiculars. So that's one thing they have in common, and that's not going to change. Alright? Now, let's apply the Pythagoras theorem. We're going to say apply PGT on both right angle triangles. The first one is right angle triangle ADC, and the second one is right angle triangle BDC. I think maybe we kind of should drag this down actually. So yeah, why not? Let's just do it. Right, so yeah, let's just erase this. Yeah, so that is pretty much it. So first, let's apply to the right triangle ADC. I'm going to take right triangle ADC, so I'm going to say in right angle triangle ADC. We're going to say that AC is the hypotenuse, you guys know, for ADC. So AC is the square of the hypotenuse, so AC square is equal to the sum of the squares of the base and the perpendicular. Perpendicular is CD, we know, but for both triangles. And for ADC, the base is AD. So AD squared, the base squared, meaning AD squared, plus the perpendicular, which is CD squared. I mean CD, so CD squared. Now this equation we're gonna call equation number 1. And now let's go to the other triangle. So we're gonna say in right angle triangle BDC. BC is the hypotenuse in this case. So BC, the hypotenuse, its square, BC square, is equal to the sum of the base, that's BD. So BD square, sum of the squares of the base and the hypotenuse, perpendicular. So the base is BD square. It's BD, so BD square we'll get. And the perpendicular is again CD, so CD square, the perpendicular square. So CD square. So now we're going to call this equation number 2. And now, if we just look at our theorem, where did our theorem go? It's all the way up there. Yeah, let's just drag that as well, because I think that's what we'll be needing now. Anyway, yeah, so this is our theorem. And now if you look at it, what you'll see is, like, what we're trying to do is just find something common that one of these equations has with the, like, original theorem. Yeah, if you don't see it, I'll just point it out. The theorem has BC squared, and so does the second equation. So what we want to do is change something in the second equation. Now, as mentioned previously several times, I think, I believe actually, that the perpendicular is, well, fixed. It's not going to change for either triangle, but BD, for example, in equation number 2, we're going to use equation number 2, this one right here, because, well, it contains BC, so, or BC squared. So yeah, we're going to be dealing with that. Now BD, it can change. CD over here, CD cannot change. This CD cannot change, but BD, we know it can change. How? If you come over here, right here, this whole length AB, there we go, and yeah, so this whole length is AB, and like what we're concerned with actually is BD, right? So like we know that AB is equal to AD plus BD, right? Maybe we should just do that. So yeah, like this part is AD, this part is BD, their sum is, what is it, guys? It is AB. So we want the value of BD. We want to see what we can replace BD with. So to do that, we are gonna change, or well, like we're gonna send 80 to the other side, because this is like an equation, right? So to get the value of something in this equation, we have to get the rest of the things to the other side, or the rest of the terms to the other side. And in this case, that's BD. So we want to get BD's value. So when we want BD's value, we'll send 80 to the other side. I'm writing BD over here. It doesn't really make a difference, but BD's over here, and we want that whatever term we want the value of, we want that term to be positive, right? So whatever the other term's sign is, we don't really like mind if they're negative or not. So right now, like AB is over here, its sign is not going to change, it's on the other side. AD is going to the other side, the side that AB is on. So 80 is positive over here. When it goes to the other side, its sign will change. It will become minus. So it will become minus 80. So BD, now we know, is equal to AB minus 80. So we are going to replace in equation number 2. We're going to replace. So we're going to say since BD is equal to AB minus AD, replace in equation number 2. So when we do that, we have BC squared is equal to BD. We're replacing with AB minus AD. So AB minus AD. We had BD squared before. Now it's going to be AB minus AD squared, or like AB minus AD whole square, plus CD squared. We know from the equation it's there. So yeah, this is our equation now. And if you remember from pre-algebra, the formula, the simple formula of A minus B whole square, which I'm going to write for you right here. Let's choose this. A minus B whole square is equal to A square minus 2AB plus B square. This is what we're going to do over here. So you can consider this term AB to be like A, and you can consider this term AD to be like B. So it's A minus B whole square, AB minus AD whole square. Nothing different, nothing difficult. So when we open the square, this will be BC square is equal to AB square, like A square. So A square is AB right now, so it will be AB square minus 2AB, so minus 2 from the formula. A's value is AB in this case, so AB into B, which, what is B? B, its value is AD, so into AD plus B square, so plus AD square, plus CD square. We know it was there in the equation. Now we're going to call this equation, this is a new equation, we're going to call it equation number 3. And now we're going to go and, you know what, let's just put the theorem somewhere like here, because we're going to have to come back to it in the future. So yeah, I just don't want to, you know, waste time coming to find it. So yeah, and now let's just take this equation, equation number 1, and paste it right here. So now what we're going to do is basically just look at these two equations. Now we want to see, like, we had to use equation number 1 somewhere too, right? We didn't do it just like because there was an equation forming, right? We kind of needed it too. And now we're going to use it. So what we want to do is look at something that's similar in equation number 3 that we can replace with in equation number 1. That, like, we can, something that's like common in both equations. So first of all, yeah, let's look at it. So in equation number 3, we have BC square is equal to AB square minus 2 into AB into AD plus AD square plus CD square. And in the first equation, we have AC square is equal to AD square plus CD square. Oh yeah, this means, I think, if you guys have caught it, if you haven't, this and this are the same. These two terms are the same. So what do? Now you can see in equation number 1, AC squared is equal to AD squared plus CD squared. So we're going to say that since we know from equation number 1, so yeah, since, oh great, that image is going to be a problem. Anyway, since what was I going to say, AD squared plus CD square is equal to AC square. Replace in equation number 3. Replace. So, yeah, let's just write equation number 3 down here. So, equation number 3 is BC square is equal to AB square minus 2AB into AD. AB square minus 2AB into AD, and BC square we have down there. And this is the part that we're replacing. AD square plus CD square, AD square plus CD square is equal to AC square. That's what we're replacing it with. We're replacing them with AC square. So plus AC square. This is basically what we get. This is like the end. We did it. Now all that is left is just to compare both the theorems, right? Like, I mean, our result and the original theorem that we founded. So, like, according to this acute angle, acute triangle, what we formed. So, what we formed was that BC square is equal to AB square plus AC square minus 2AB into AD. Now, if we compare this, we have BC square is equal to AB square minus 2AB into AD plus AC square. So, yeah, they're pretty much the same, just I mean, they're exactly the same, just that there's a bit of a difference in the position of AC square and minus 2AB into AD. But now I just want to give you like a quick little summary to help you understand this theorem and hopefully make it stick. So yeah, the square of the side that's opposite to the acute angle in an acute angle triangle, which if we considered angle A, which is right here. So the side that's opposite to that is side BC. So BC square right here is equal to the sum of the squares of the sides forming the acute angle, and side AB is forming the acute angle, and side AC is forming the angle A, which is acute. So the sum of their squares, AC square plus AB square plus AC square, subtracted by twice the length of one side and projection of the other. So minus 2, which is right here, and the length of one side, our axis, our horizontal axis. In this case, we're viewing with AB on the horizontal axis, so AB into AB, the length of one side, and the projection is always, of the other one that's not on the horizontal axis that we're looking at from our perspective, and that is in this case AC. So AC, its projection is AD, as we have down there. So that is basically this theorem, the second theorem, and yeah, that's pretty much it. We're done. So now you got another theorem under your belt, so congrats. And my advice is, again, just please practice this several times, and yeah, eventually you'll be able to know exactly what you're doing. For the first few times you might have a bit of a confusion, but like this video was supposed to build your concept, and you should not have any confusions. But if you still do, you can ask me any questions you have. Leave them in the comments, right? And I'll get back to you. And if you need advice in general, I can also offer that too. So just leave them in the comments again. And yeah, this is the second theorem, and hopefully I'll be uploading the third in a few days, and I recommend you check that one out as well. And if you still haven't checked out the first theorem, I recommend you go now and check that. And yeah, check my other videos too if you need help with quadratic equations, math, or well, any subject. I'm trying to do like all the subjects. And yeah, subscribe for more videos, and better yet, ring the notification bell, I'd say. And like this video and share it with someone that is struggling, or anyone actually, because it always helps. Knowledge helps, right? You can never have too much knowledge. So yeah, that's pretty much it for this video, and thanks for watching, and see you next time.